Let's do one more example of using residue theory to find the integral of a rational function of sines and cosines. This problem is very similar to the one in the previous video. I have dz over 13 plus 12 cosine theta. This time though I'm squaring the denominator, so that my pole will have order 2 rather than order 1. So to begin with, let's make the standard substitution in this case. The cosine theta will be replaced by half of z plus 1 over z, and the d theta will be replaced with dz over I times z. So the d theta gets replaced by dz over iz, and this cosine theta gets replaced by half of z plus 1 over z. And now I'm integrating over the unit circle in the Argand plane. Okay, let's spend a little bit of time simplifying. We can factor the 1 over I to the front again. Inside the square, half of 12 is 6. And 6 times z plus 1 over z will be 6z plus 6 over z. Now once again, I'd kind of like to distribute a z in here to get rid of the z in the denominator. But since this is squared, I really need to multiply in a z squared. So let me multiply by an extra z over z, so that's a z squared, so that I get 1 over I times the integral over the unit circle of z over, I'm going to rearrange a little bit inside. 6z times z is 6z squared plus 13z plus 6. And the polynomial inside parentheses is the same one we had in the previous example. So we know how it factors. It factors as 3z plus 2 times 2z plus 3. So in this problem, our function f is going to be z over 3z plus 2 squared times 2z plus 3 squared. This one still has 2 poles. One of the poles is at negative 2/3. The other pole is at negative 3/2. That's the same as in the previous example. The difference is these poles are of order 2 rather than order 1. So we're going to have to work a little bit more in order to find the residues. So first, let's apply the residue theorem. This entire integral will equal 2 pi I times the sum of the residues inside the circle. There's only one residue. There's only one pole. So it would be the residue of the function at negative 2/3, where f, again, is the function I've circled here. So we need to do some scratch work to figure out what this residue is going to equal, remembering that this is a pole of order 2. Here's our scratch work. The residue of the function at negative 2/3 will be the limit as z goes to negative 2/3 of z plus 2, the derivative with respect to z, of z plus 2/3 squared times f of z. Let's see if we can simplify that a little bit. This is the limit as z goes to negative 2/3 of the derivative with respect to z of z times z plus 2/3 squared over 3z plus 2 squared times 2z plus 3 squared. I'd like to cancel in a similar way to what I did last time. It feels like this term factor up here should cancel with this down here, but I need to factor this 3 out. But remember, the 3 is squared. So this expression here is the same as 3 squared times z plus 2/3 squared. So then if I want, I can cancel this factor with that factor. And I get the limit as z goes to negative 2/3 of the derivative with respect to z of z over 9 times 2z plus 3 all squared. Wow, I need more space for my scratch work. So next we need to take the derivative of this function with respect to z, and then finally we need to take the limit as z goes to negative 2/3. So let's apply the quotient rule. I can factor the 1/9 out and just take the derivative of the z over 2z plus 3 squared. Using the quotient rule, I have 2z plus 3 squared times the derivative of the top, which is 1, minus the top, which is z, times the derivative of the bottom, bringing out this 1/9, which is 2 times 2z plus 3 to the first, times the derivative of the inside, which is 2, all divided by 2z plus 3 to the 4th power. We can simplify this a bit. Notice that I have a factor of 2z plus 3 in each of the terms on top, as well as on the bottom. So I can cancel one of those, one of these, one of those, and one of those from top and bottom. What I'm left with is 2z plus 3 minus 2 times 2 times z is 4z, all over 2z plus 3 cubed. Continuing, that'll give me 1/9 times the limit as z goes to negative 2/3 of, combining like terms on top, I have 3 minus 2z, and on the bottom, 2z plus 3 cubed. Well, finally, we can use direct substitution. Plugging in a negative 2/3 for each z, I get 3 plus 4/3 on top. Inside the parentheses downstairs, I have negative 4/3 plus 3, all cubed. And now let's do the arithmetic. 3 plus 4/3 is 13 over 3. On the bottom, 3 minus 4/3 is 5/3. So 5/3 cubed. So continuing to simplify, I have 13/3 over 9 times 125 27ths, which is 13/3 divided by 125 over 3, which is finally 13 over 125. So the residue of the function at -2/3 is 13 over 125. And finally, we can plug that back in up here. So the integral, which was in black, canceling the i's, is 2 pi times this residue that we just calculated, 13 over 125, which is 26 pi over 125.